All right, in this short video, I want to show you a tactic that lets you generalize the IH explicitly and manually rather than relying on a late intros to have a general IH. Um, so it's just like often the case that you have a bunch of things that you're quantifying over, and the natural way that you want to state the theorem has the variable you want to do induction come later, right? Not an uncommon thing. And like you could always rearrange it so that the thing that you want to do induction on comes earlier in the list, but like sometimes it's just like not the natural phrasing. So like you'd like to be able to say it the way you want it and then do it that way. So just for the sake of argument, suppose that we wanted to do induction on M here for some reason. Like that felt important to us. This is like a kind of weird canned thing, but like, okay, let's see what happens. So if we go through, we'll get to here. And if you look at the IH, you see we have the same problem, but kind of like mirror image, where now we have this fixed n. And so then when we get to this point, we apply f equal, and then like now we're stuck, right? We can't apply IHM prime because it doesn't match, right? So that sucks. Like we'd like to be able to do induction on M. So what you need is a way to sort of unintros things. You need to sort of like undo the fact that you've introduced something. So there's a tactic that does that. It's called generalized dependent. Um, excuse me. Every time. Every time. Okay, so it's called generalized dependent. So let's see. So let's do it again. We're going to do induction on M to do the proof. But what I want to do before we do induction on M, I want to say, let's get N back out of our context. I want to pretend like I never quantified over it. So if you look at our context, we know about some M, and now we're proving that for all N that's in that, double N equals double M, N equals M. So what we've done is we've just undone the intros and sort of only introsed M. That is, I think, pretty neat. So now we can do induction on M. And when we get down here, you can see that we have this nicely quantified IH. Again, sort of we're in mirror image land where N is the other thing. And our proof goes through just fine. So this is, I think, a super convenient tactic to use. I'll often use it even when intros order would work because it's like easier for me to introduce everything, think about what I want to do, generalize away the things I don't want, and then go on. Now, it might be the case that you need to generalize more than one thing, and so then you might need a couple of generalized dependents. If you then want a particular order, you need to generalize dependent in the reverse order, because each time you generalize, it's going to stick something onto the front, so it's kind of like a stack. You'll see what I mean when you get there. Not a big deal. You'll figure it out. So this tactic, generalized dependent, is sort of the key move here. Handy thing to have in your back pocket means you don't have to be so clever with your introses. Okay. Any questions about this tactic? Hit me up on Zulip. Happy to talk about it. Maybe one more thing I'll show actually. If we intros all the way, NMH, and then I do generalized dependent, what's going to happen to H? Notice that the H, even though we only talked about N, the H got stuck back on. That's the meaning of the dependent here. So when we say generalized dependent, we mean, hey, I'd like you to generalize N and everything that depends on N, right? This proposition, the assumption that we called H, right, double N equals double M, you can't even utter that until you know the name N. So if we're going to generalize N, we have to generalize that too. So I just want to make it clear that you can really undo a lot in sort of one go with a tactic like this. Okay, that actually is everything I wanted to say on this. In the next video, we'll go over like some practice about like exercises you have to do on this homework. Talk to you soon.